So next speaker will be Vincent from Total Energy. Yeah, the title is the technical economic analysis and scale up that. So yeah, Vincent, please.
Good afternoon again. So now we go a bit in the future. We are leaving Chile, the 3 megawatts, and now we fly to the 500 megawatt thermal or 200 megawatt electric unit. So just before speaking about the technico-economic analysis, we let the floor to Patrice, who will explain how all this modelization has been used to design this big equipment for the 500 thermal megawatts.
So the objective of the study was to provide this EA, as Vincent said, at large scale. So we have addressed many design cases relevant for industrial needs. And the our objective, of course, is to benchmark CLC technology with reference technology, which will be described by Vincent later. So I just want to quickly introduce the item of the TEA by saying that we need some tools to do the process simulation and to do the TEA. So first, we developed, in fact, a fuel reactor model at industrial scale, which then be integrated in a complete process simulation of CLC plant. So I will show you how we did, and then Vincent will speak about the benchmark of CLC technology, with the economic evaluation, the benchmark results, and the environmental perspective with life cycle assessment. So yes, this work has been done in collaboration with Nicolas. So it concerns the multi-scale approach for the fuel reactor modeling at large scale. So to elaborate a fuel reactor model, we decide to follow a strategy in 4 parts. The first part consists in developing a model, first model, based on experimental results coming from our batch unit. Then, with this first model, we try to validate it with some results obtained in a bigger unit, the continuous unit we have at IFPA. The third part consists in upgrading this model to industrial scale by adding an appropriate hydrodynamic. In fact, the hydrodynamic we have in the fuel reactor at small scale, so at pilot plant scale, is not the same as the one we have at larger scale. So we need to adapt it, to adapt the correlation. And then the final validation will be done based on the demo unit results. Here, on this slide, we have just an overview of the fuel reactor model. As you can see, there are many banks, reaction banks with all the reactions, another one concerning the kinetic parameters, then a part dedicated to the calculation of the source terms of the mass balance, taking into account the solid which are in the fuel reactor. And the last one, the orange one, is the hydrodynamic bands, which contains all the correlations for the model. So in the final version of the model, we want to simulate types of hydrodynamics, a bubbling bed regime, and a turbulent bed regime. Yes, because the demo plant and an industrial unit, as Nicolas said, works in a turbulent regime. At the top of the slide, we see some graphics to show that the first model is well correlated with experimental results. So, as the first approach, we have a good prediction of the parameters impact in batch conditions. So we have a first model which can be then validated on the other two. So at the bottom of the slide, we see the good correlation with this pilot scale because the experimental data are already in correlation with simulated data for different parameters such as the vector conversions, R0 delta X, and other parameters. So we think after those two steps of scaling up, that the physics of the model is well represented. As I said previously, we need a third part which consists in implement some correlations for turbulent fluidized bed. So the work has been done by a PhD student from Hamburg University, Tom Widwart, who developed some correlations for this type of hydrodynamics. So it has been implemented in the code, and as we can see, the first results given by the model, we have a vector conversion of 65%, whereas the target for this type of reactor in our configuration is 60% in one stroke. So yes, to finish on this point, we can say that the model is ready for validation and cheers, and we will use the new results obtained on the demo plan to finalize this validation. Then with this model, we can implement it in the process simulation, complete process simulation, before doing the TEA. So this work has been done in collaboration with Catherine Laroche from IFPN and Xiao Fu and Raoul Anataraman from CIPER. For this process simulation, we consider two design cases. A refinery case with a generation of 100 ton per hour of steam and 50 megawatt of electricity. And for our case, the second application case, it's only a production of 200 megawatt of electricity. So this work, this second work consists in having a complete process simulation of the CFC, including the reaction section, the flue gas treatment, the heat recovery and production of steam and electricity, and finally the CO2 capture and compression. So the simulation has been done with Aspen Plus software. Here we have a picture of the CFC case simulation with all the elements of the simulation, and we recognize the blocks I have just detailed before. Just another specific point on the strategy we adopt for this simulation. So the objective was to have the Aspen Plus simulation on the left-hand side, and we need to couple different tools to have this complete simulation. So we use our hydrodynamic models to estimate the carbon stripper and cyclone efficiencies. So these results are injected in the complete simulation. And we use also the hydrodynamic model to design the reactor, to evaluate the residence time of a solid in this reactor. And we also use the fuel reactor model I have just described before to simulate the reactions in this fuel reactor, so to determine the fuel conversion per gas. And this result is also a parameter for the Aspen Plus simulation. So by coupling different tools, we are able to simulate the complete CFC process. And to finish my part, so just an overview of the reactor design to have an idea of the size of the reactors. So on the left-hand side, we have the Hell reactor. So the size of the Hell reactor for design cases, power and refinery, compared with the demo unit, 3 megawatt. So as you can see, our demo unit is very representative of the industrial scales, with a height close to the industrial case. And for the fuel reactor, we can have a look to the diameter of the fuel reactor. So for the industrial case, we are between 9 and 12 meters. And in our case, in the young, we have 1.5 meters. And so the phenomena, the hydrodynamic should be representative in our case, in our demo plan, compared to the industrial case. So to summarize the requirements for TEA, we developed a set of tools coming from the design study, which permits to describe finally all the reactors and all the main equipments. So as we know how they are being designed, we are able to estimate the cost of the equipment. And finally, the process simulation with the fuel reactor model is available now. So the whole performance of this process are known from the fuel to the energy generation. So let's continue this presentation with the TEA.